Welcome back. Let's assume that we have a rocket here. And let's assume that the air is very thin already, meaning that we have enough altitude and the density of air is very thin. It means that we can neglect the aerodynamic forces that are acting on the rocket. So we assume no aerodynamic forces. We will only consider two forces here. The force of gravity or weight that points down through the rocket's center of gravity, or CG, and then the thrust force is another force that we will consider, and it is provided by the rocket's engine. However, since the engine is slightly tilted, the thrust force vector does not point through the rocket, but rather it tilts slightly away from the rocket in order to rotate this rocket counterclockwise a bit. The rocket itself is 50 meters long, and then this center of gravity is located at 30 meters from the base of this rocket. And with these two lengths, we are not assuming the engine and also the origin of this coordinate frame. It's also put here at the base of the rocket. We can call this point O. The rocket itself is tilted at 70 degrees from the positive x-axis, and the thrust force vector is 60 degrees from the positive x-axis. Both vectors, the weight and then the thrust vector, they can be decomposed parallel to the rocket and perpendicular to it. We just use this parallelogram rule where we obtain two components that are perpendicular to each other. Also, the mass of the rocket is 10,000 kilograms and gravitational acceleration is minus 9.81 meters per second squared, meaning that it points down in the same direction like this W vector. And so the W vector equals the mass of the rocket times g. Well, it's essentially 0I minus 98,100 J newtons. And the magnitude of it would be 98,100 newtons. And now here's the question. What thrust force do you need so that the component of this thrust force that is parallel to the rocket, this one here, so that it would be equal to the component of the weight vector that is parallel to the rocket as well? Now, of course, their directions are opposite, but I want their magnitudes to be the same. So I want this to be equal to this. Of course, it's not that difficult to do. From geometry, you can see that since you have 70 degrees here, then you have 20 degrees here between the weight vector and the rocket. You can think of it like this. If this 70 degrees, if it's 90 degrees, then this angle will be 0 degrees. And now since this is 70 degrees, this is 20 degrees. Also, this angle here that we can call alpha, we can very easily calculate that alpha equals 70 degrees minus 60 degrees, which equals 10 degrees. So you have 70 degrees here, 60 degrees here, and their difference is alpha. You know that W parallel equals W times cosine 20 degrees. That's 98,100 times cosine 20 degrees. Approximately it equals 92184 newtons. And if you're interested, then you can also calculate the component that is perpendicular to the rocket. This component equals W times sine 20 degrees, and that approximately gives you this answer. And then, if you want this law to hold, then you can write T parallel, which is equal to W parallel, it equals T times cosine 10 degrees, and it equals this number here, so this one, and from that you know that T equals 92184 over cosine 10 degrees, so t approximately equals this one here. And then if you want to calculate t perpendicular, which is this one here, it's perpendicular to the rocket, then you would write t times sine 10 degrees, so it's this one here, so it's 16254 newtons. Okay, so that was easy, of course. But now let's do it slightly in a different way. It will be a more formal and longer way, and you don't really need it if you work in 2D, but it's way more helpful if you operate in 3D. So let's do that in the next video. Thank you very much. Welcome back. So let's now solve this rocket exercise and get the same answers, but using a more formal method for that. Let's imagine that you have two vectors, A and B, and you have an angle between them, theta. One way you can multiply two vectors is like this. Vector A dot vector B equals the magnitude of vector A times the magnitude of vector B times cosine theta, and the theta being the angle between the two vectors. That's how this product is defined, and it's called the dot product. That's why you say A dot B. Theta here can vary between 0 degrees and 180 degrees. It's just how we define the dot product. It's a definition. Also note that even though a vector has several dimensions, but when you take the magnitude of your vector, then that magnitude is a scalar quantity. So if a vector equals axi plus ayj plus azk, then it has 3 dimensions. But then the magnitude of this vector, that you can calculate like this, it has only 1 dimension. So this thing is a scalar. And so what you're doing here, you're multiplying one scalar by another scalar, and then this cosine theta, it's simply some kind of ratio. So if this is your right triangle, this is theta, this is A, B, and C, so cosine theta equals A over C. So it's simply a ratio. Therefore, the result of a dot product is a scalar quantity, which makes sense because you have one scalar times another scalar times some kind of ratio. So you have to get a scalar. In 2D, it's very easy to see what the dot product does. If I slightly turn these two vectors like this, then I will have it like this. And so if I write B times A times cosine theta, it doesn't matter whether I write A times B or B times A, and now I'm going to put parentheses here, then essentially what I have done here in this parenthesis, I have obtained a component of the vector A that is parallel to the vector B, and then I only end up multiplying this vector B by the component of A that is parallel to B. So I end up multiplying two arrows in the same direction. The white arrow, which is the B, and then the red arrow, which is the component of A parallel to B. So essentially I have A parallel times B. You can also think of it in a different way. I can rotate these two vectors like this. So I draw my two vectors like this. I have theta, and then the equation can be written like this. So this will be in the parentheses. And so with these parentheses, I obtain a component of this vector B that is parallel to A. And you're still multiplying two arrows in the same direction. But now it's B parallel times A. But in the end, it doesn't matter because AB times cosine theta equals BA times cosine theta, which means that A dot B equals B dot A. That's called the commutative law. In the end, you still get the same result. When you obtain the component of B parallel to A, then that can also be called like this. You are projecting B onto A, and then vice versa. If you obtain the component of A parallel to B, then you are projecting A onto B. In both cases, you have right triangles here. In this case, and also in this case. But now, let's generalize the dot product and try to write it using the unit vectors, considering that the A and B vectors are both three-dimensional vectors. In other words, if I say that this is the A vector, this is the B vector, then their dot product will be like this. A dot B, that's the A vector, dot, that's the B vector, and so let's write it out. So I'm going to multiply this one by all these three components, and then I will have this one here. And now I will take this component and then multiply it by all these three components in the B vector. And so I will have this result here. And then I'm going to take this component and I'm going to multiply it by all of these three B components. And so I will have this result here. And now you have many terms here, but in each term, these are scalars. They have no direction, and therefore you just get a scalar when you multiply them together. But then these are vectors. They do have a direction. These are your unit vectors. Their magnitudes are 1, but they have a direction. Remember, this is your x, y, and z coordinate frame. So this is your I unit vector, this is your j unit vector, and this is your k unit vector. And so they have their directions. And so, for example, what would be this one? I dot I. Well, it would be the magnitude of I times the magnitude of I times cosine and then the angle between them. So that would be 1 times 1. And then what's the angle between I and I? Well, they both point in the x direction. So the angle is 0 degrees. So cosine 0 degrees, which is 1. So you have 1 times 1 times 1. And so you get a scalar, which is 1. So here you have ax times bx times 1. How about I dot j? Well, that would be 1 times 1, because both of their magnitudes are 1s, times cosine, and then the angle between them. But what's the angle between I and j? Well, it's 90 degrees, right? So it's going to be cosine 90 degrees. It's 0. So I dot j gives you a scalar which is 0. So this one will be 0. And how about I dot k? Well, again, it gives you 1 times 1 times cosine, and then the angle between I and k is 90 degrees. Again, that gives you 0. Therefore, this one is 0. Now you have j dot I. Again, since they are perpendicular to each other, you know that it's going to be 0. Now j dot j, they both point in the same direction. The angle between them is 0 degrees. So it's like I dot I. So that means that this one is 1. Then j dot k, the angle between them is 90 degrees. So it's 0. You can see it here. You have 90 degrees. So you have 90 degrees pretty much everywhere. And so k dot I, that's 0. K dot j, that's 0. And then k dot k, that's 1. And so thanks to that, you can forget about this term, then also this term, also this one, and this one. Because if you multiply something by 0, you will get a 0 term. So your end result will be ax bx, which is this one, because you have ax times bx times 1, so you get a scalar, plus ay times by plus az times bz, this one. And note that this is not a vector, this is a scalar. And there you go, now you know how to calculate the dot product of a vector if you have their I, j, and k components. And especially in 3D, it's a lot easier to do it like this. But also if you have a two-dimensional case, then the logic is the same. So if your A vector does not have a third dimension, and your B vector does not have a third dimension, then in the end, you will have this result. You multiply the x components of both vectors, and then you multiply the y components of both vectors. And the result that you get from here, it will be equal to this result here. But the good thing about this formulation is that when you have a three-dimensional vector, or maybe in another context, a higher dimensional vector, maybe a 4 or a 5 or a 6-dimensional vector, and you have to take their dot product, then that's the formula that you would use. But now you see where that formula comes from. And now you might ask then, okay, that's all very nice, but how does it relate to statics and to this rocket example? Well, here's the thing. What if your B vector is some kind of general unit vector? So you have your A vector, and then you have your B vector, which is a general unit vector. The magnitude of this general unit vector is 1. The angle here is theta, and then I'm going to say that this is my J vector, and this is my I vector. Then if I take A dot B, then essentially I will have A vector dot, then this general unit vector in the B direction. So that's the magnitude of A times 1, because that's the magnitude of this general unit vector, times cosine theta. In other words, I can write 1 times A cosine theta. And so right here, what I have done, I have obtained the component of A, let's call it A parallel, that is parallel to this general unit vector UB. And then I multiplied by 1, because again, that's the magnitude of UB, which means that you have obtained a component of A in the direction of UB only. And that's it. But now you know that you can achieve the same thing if you first decompose your A vector into its Cartesian components. So one will be in the I direction, so this is your AX, and the other one will be in the J direction, so this is AY. And you do the same thing with this general unit vector. So this one is UBX, and this one is UBY. And so using this Cartesian dot product formula, you can write it out like this. AX times UBX plus AY times UBY. And without knowing the angle between these two vectors, you can obtain this dot product. And so with this formula, you can take a vector and you can project it onto a different line, like for example, this line, if you know the general unit vector of that line in your Cartesian frame. And we can use it here in this rocket example. I have a thrust force here. That could be your A. I can write this thrust force in this form. So essentially, this component here, it would be my Tx, and then this component here, it would be my Ty, and then I can have a general unit vector in this direction along the rocket. So let's say that the tip of the rocket, we call this point A, and so this unit vector here, that we can call the unit vector in the A direction with respect to O, with respect to this origin, we can take this unit vector and also decompose it into its x and y components. So this would be its x component and this would be its y component. And now what will you get when you have t dot and then this general unit vector? You will have tx times the x component of the general unit vector plus ty times the y component of the general unit vector. And since the magnitude of this general unit vector equals 1, then essentially what you're doing, you're obtaining the component of the thrust force along the rocket. Essentially, you get this one here, t parallel. So instead of just multiplying t times cosine alpha that we did here first, this was the formula, we can get the exact same thing using the dot product. Welcome back. So in this video, I want to numerically show you that when you use the dot product to solve this rocket problem, then you will get the exact same solution. So remember, we had to find our thrust value so that T parallel would be equal to W parallel. And W itself was 98,100 newtons. So first of all, what I want to do, I want to obtain this W parallel using the dot product. For that, I need to obtain a unit vector in this direction. So first of all, the position vector of this O point, let's call it O with respect to O, it's 0i plus 0j. And then the position vector of this point center of gravity, let's call it CG, with respect to O, with respect to this origin, that's 30 times cosine 70 degrees times I plus 30 times sine 70 degrees times j. So this position vector here, it goes from O till CG. So it goes right here. This is this one. But now I'm going to calculate a displacement vector, which will be RO with respect to CG. So it's this position vector minus this position vector, and it looks like this. So you end up having this displacement vector, which is essentially the same vector like this one here, but it's in the opposite direction. It goes from CG till O. Then the magnitude of this vector is 30 meters. You can see it even without calculations, because the distance from O till CG is 30 meters, which means that the unit vector, O with respect to CG, it's this one. In other words, what you have is this one here. You can cancel out all these 30s here, and so in the end, this is your unit vector in the direction of O with respect to CG. So it's this unit vector here. And now, since you know that your W vector is 0i minus 98,100j newtons, you can get your W parallel using this dot product formula. So this vector dot UO with respect to CG. So you have 0 times minus cosine 70 degrees plus minus 98,100 times minus sine 70 degrees. And that will give you 92184 newtons. And as you can see, when we made those calculations earlier in an easier way, then you got the same number, 92184 newtons. So you got the same answer. And since we have this relationship here, that means that this thing is also this one. So you have your W parallel or T parallel, and then you have your unit vector from CG towards O, but now we need to relate this thrust force with this T parallel. For that, we need a unit vector from O in the direction of CG. However, it has the same line of action like this unit vector, only it's in another direction, which means that UCG with respect to O, it's the same vector, it's just instead of minuses you have pluses here. So now this one, it's this one here. And now we need to decompose this thrust force. It equals T times cosine 60 degrees I plus T times sine 60 degrees J. And now T parallel equals the thrust force dot UCG with respect to O. It equals this one, which is 92184 newtons. You can factor out T, and so your thrust force equals 92184 over all this, and that will give you 93606 newtons. As you can see, it's the same one that we had before when we made those calculations using an easier method. Now, it's important that you understand the difference between two things. Here, we had the thrust vector dot this unit vector here, which points in another direction. And as a result, you obtain the component of the thrust vector along this unit vector. But now, let me obtain another unit vector in the direction of the thrust vector. This unit vector is cosine 60 degrees times I plus sine 60 degrees times J. You get it with this formula, T vector over the magnitude of T vector. And now if I write T times and this unit vector T, then this is different from this one here. Here, this unit vector already points along this thrust force, and this one is the magnitude of the thrust force. And so the objective of this operation is to decompose this thrust vector. In other words, we get this. So here I'm simply multiplying a scalar by a vector, and the purpose is to transform the scalar into a vector. In other words, the purpose is to decompose this magnitude. But here, I don't have a scalar times a vector. I have a vector dot another vector. And now this unit vector is in another direction, not in the direction of the thrust force, but it's in another direction. And the purpose of this operation is to project the thrust force onto the line parallel to that other unit vector. And here, the result is a scalar. So here, I'm decomposing the existing vector, and here, I'm projecting my vector onto another line. So let's say that now, I want to take this T parallel, which is a magnitude, along the rocket, and I want to decompose this T parallel into its x and y components. So I need to do something like this. T parallel vector equals the magnitude of T parallel times this general unit vector, this one here, that points in the same direction like the T parallel vector. Or I can replace this T parallel with this expression here, and I can write T vector dot UCG with respect to O. So here I'm dotting two vectors, I get a scalar, and then I multiply that scalar by the same unit vector. And if I do that, then in the end what I will get is this answer here. Now this T parallel that I have here is decomposed into its x and y components. So I simply want you to see the difference between this operation and this operation. And now since you have your thrust force in this Cartesian form, and then T parallel in this Cartesian form, then since thrust force equals T parallel plus T perpendicular, which is this one here, now you can find this T perpendicular. It equals T vector minus T parallel vector. That will give you this result for the I component and this result for the J component, and that's your final answer. And now if you take its magnitude, then you get 16254 newtons. And that's exactly what you got here in your previous calculations, 16254 newtons. And you can use the same method to calculate W perpendicular, because you know that W vector equals W parallel vector plus W perpendicular vector. Again, this approach is more tedious compared to this one here that we did before, but remember, this is a 2D problem. I will give you a 3D problem very soon. Welcome back. Before I give you a 3D problem, I want to caution you against something. When projecting forces onto lines in a different direction, then you have to be careful here. It gave you the correct result with the rocket example. But consider these two cases. You have case A and case B. You have 90 degrees here. You have 60 degrees here. In both cases, you have 30 degrees here. And so essentially, these are beams that are against walls. And so a force is applied here, and the angle is 30 degrees. And the same thing here, the same force is applied here, and you have 30 degrees here. If I ask you what compression forces both beams experience in both cases, then in case A, you can find that using the dot product. You define a general unit vector along this beam here. Let's just call it U. And then if you write F vector dot and then this U vector, well, then you will get F parallel, which is the magnitude of this component here. And then later on, you can find the magnitude of this vector, which is F perpendicular. Essentially, F force equals F parallel force plus F perpendicular force. And so you already know how to find this one. You have to decompose this vector and this vector into their x and y components, and then this will be your F perpendicular vector, and then later on you will find the magnitude of this perpendicular vector. However, that's only in case A. In case A, it would be correct because the beams themselves are perpendicular to each other. However, that's not the case with case B. In case B, if you use this dot product to project this force onto this beam, then your F parallel here, it will be the same that you had in case A. You would have 90 degrees here, just like you had here. But now, in this case, this F parallel would be wrong. It would not be the correct compression force that this beam experiences. And that's because these two beams, they are not perpendicular to each other. They are only at 60 degrees from each other. Here, in order to decompose this force vector along these two beams, you have to think in terms of having a coordinate frame that goes along those beams. So this is 60 degrees here, then this is your force, here you have 30 degrees, and so you would decompose this vector like we learned at the beginning of this section. You have one component along the u-axis and another component that is along or parallel to the v-axis. That was the case when we were adding vectors using the triangle or the parallelogram rule. And now your F parallel will obviously be different. And also your F perpendicular will obviously be different. So in this case, this is the compression force in this beam, and this is the compression force in this beam. If you shift it here, then it will be like this. And so this compression force, it's obviously smaller than the one that you would get using the dot product. Because if you had used your dot product here, then you would have received this component. But that would be wrong. In reality, this component is smaller. And it kind of makes sense, because due to the fact that these two beams are closer to each other, in this case, in case B, this second beam will take some of the load away from this lower beam. In case A, this beam is further away from this beam in terms of this angle. So this beam needs to take a bigger component from this force vector. However, in case B, the second beam is closer to this force vector, so it will take a bigger component from this force vector. And thanks to that, this beam needs to take a smaller component from this force vector. So intuitively it makes sense why this component is smaller compared to this component here. So this is where you have to be careful. The projection using the dot product is only equivalent to decomposing vectors in cases like this, or like in the rocket case that we had. Because essentially the case with the rocket was that we could treat it as one beam. So if you forget about this beam here and you only focus on the lower one, and then you imagine that it's a rocket, then it's a very similar case. However, in cases like this, you should not use the dot product. But now let's do a 3D problem where we will use the dot product. Let's do that in the next video. Thank you very much.